Before the Big Bang, it's crucial to clarify definitions. If the Big Bang is defined as the moment when the universe was extremely hot and dense, evidence supports this, as we can observe its remnants in the sky. The leading theory explaining how the universe reached this state suggests a preceding phase known as inflation. Scientists have long pondered what existed before the Big Bang, and recent discoveries have unveiled a startling possibility. Brian Cox has proposed that something unsettling existed prior to the Big Bang, a cold, empty universe expanding at an extraordinary rate before slowing down. The energy driving this expansion was released into space, heating it up and forming the particles that constitute everything we see today. This event is what we call the Big Bang. This idea extends into the theory of eternal inflation, which posits that inflation continues indefinitely, ceasing in certain regions to create universes. This implies that our universe is just one of many, forming part of an infinite fractal multiverse. The concept of absolute nothingness seems more theoretical than real, as even in an ostensibly empty universe, energy persists. Even if all matter, radiation, and external influences are removed, quantum fields and fundamental physical laws remain, making true nothingness impossible. The universe never truly reaches a state of void. Something always endures. Even in an empty universe, expansion would generate radiation, challenging our conventional understanding of emptiness. Scientists have questioned whether the universe could have emerged from nothing, but physics suggests that an absolute void cannot exist. Even if all quantum fields reach their lowest energy state, a residual zero-point energy would remain. As the universe expands and cools, radiation will eventually dominate, with dark energy becoming the primary force shaping cosmic evolution. Before the Big Bang, during cosmic inflation, the universe expanded rapidly due to inflationary field energy, akin to today's dark energy but much stronger. This raises fundamental questions about the universe's origins. Did time have a beginning? Understanding this requires distinguishing three key ideas: the hot Big Bang as a description of the universe's early state, cosmic inflation as the process that set the stage for the Big Bang, and the broader question of the ultimate beginning. In the early 20th century, major discoveries shaped our understanding of cosmic expansion. Alexander Friedmann, using Einstein's equations, showed that a universe filled with matter and energy could not be static but must either expand or contract. Observations by Henrietta Leavitt and Edwin Hubble confirmed that galaxies were moving away from us, indicating that space itself was expanding. Rewinding this expansion suggests that the universe was once denser, hotter, and ultimately reached a state of infinite density and temperature, leading to the original idea of the Big Bang. This theory predicted key features of the early universe, including cosmic expansion, the formation of structures like galaxies, and the existence of cosmic microwave background radiation. These predictions were later confirmed, solidifying the Big Bang theory as the dominant explanation for the universe's early history. However, by the 1960s and 1970s, certain paradoxes emerged that the Big Bang alone couldn't explain. The horizon problem questions why regions of the universe that never interacted have uniform temperatures. The flatness problem asks why the universe's expansion and gravitational forces are so precisely balanced. The monopole problem challenges why no exotic high-energy remnants from the early universe, such as magnetic monopoles, have been found. In 1980, Alan Guth proposed inflation as a solution to these puzzles. Inflation suggests that an early phase of rapid expansion could have stretched the universe, explaining its uniformity and apparent flatness while diluting any exotic relics. This theory has since become central to modern cosmology, preventing the universe from reaching excessively high energies or temperatures. The maximum temperature reached after inflation avoids the formation of these remnants. Inflation not only explains these phenomena but also presents a compelling alternative to the standard hot Big Bang model. It also addresses how a uniform and isotropic early universe could be reinstated after inflation. It became evident that inflation could act as a quantum mechanism for seeding the universe with initial imperfections, leading to the intricate structures we observe today. In the 1980s, inflation theory made precise, testable predictions about the beginnings of cosmic structure, detectable in both the cosmic microwave background and the large-scale layout of the universe. These predictions, crafted decades ago, have been validated by observations from the 1990s to the present day, encompassing an almost scale-invariant spectrum of imperfections, variations in density and temperature, and entirely adiabatic density irregularities. In essence, fluctuations on scales larger than what a signal traveling at the speed of light in an expanding universe could generate, and a maximum temperature limit for the universe during the hot Big Bang, are notably smaller than the Planck scale. Because inflation involves a rapid expansion of space rather than culminating in a singularity like the original Big Bang model, it presents an alternative depiction of the beginning. Instead of time and space gradually emerging from a single state, inflation proposes a rapid expansion leading to the Big Bang. This raises a fundamental question about the actual beginning of the universe, if such a notion even makes sense within the framework of the hot Big Bang. Without inflation, we could trace back and reach a singular state where the universe's size approaches zero in a finite time. However, inflation complicates the scenario. Its exponential growth makes it challenging to trace back to a singularity, as reaching a state where the universe had zero size would require an infinite amount of time due to the exponential nature of inflation. Adding to the complexity, the observable evidence for inflation, such as quantum fluctuations leaving imprints on our visible universe, corresponds to just the final /10⁻32 seconds before inflation leads to the hot Big Bang. If we were hoping to delay the start of an earlier grand event, inflation ruins those hopes. There's nothing observable that gives us clues about what, if anything, caused inflation. A fascinating aspect of inflation is called eternal inflation. When exploring how inflation works, almost any model that effectively addresses the issues with the original Big Bang and creates the necessary quantum effects to initiate the universe with imperfections will result in a scenario where, while inflation ends in certain areas like our own, there will be countless more surrounding regions where inflation continues, creating more space that keeps expanding. Essentially, once inflation starts, it wipes out any information about what existed before, and the inflationary state will persist indefinitely into the future. At times, quantum fluctuations, akin to those shaping the universe's structure, cause certain areas where inflation ceases, resulting in a hot Big Bang. However, these regions are far fewer compared to those where inflation persists indefinitely. Notably, no two separate regions with Big Bangs will ever overlap because the expanding universe drives them apart. Despite its appeal, eternal inflation has limitations. It's eternal only into the future, not into the past. In fact, it's been demonstrated that inflationary spacetime doesn't extend into the past infinitely and must have originated from a prior non-inflationary and possibly singular state. The issue of past time-like incompleteness can't be avoided by considering alternatives like bouncing cosmologies or cyclic cosmologies, as they face similar challenges. However, this doesn't necessarily imply that the universe originated from a singularity. While it could have, it's not a strict necessity. For example, one can envision a spacetime resembling the past where inflation takes place by modeling the universe's expansion rate through a scale factor composed of a growing exponential plus a constant, rather than just a pure growing exponential. In essence, the hot Big Bang, while our most accurate model of the early universe, wasn't its absolute genesis. There's a limit on how far back we can extrapolate the temperature and density of a matter and radiation-filled universe. Prior to the hot Big Bang, there existed a period of cosmic inflation, which initiated and led to the hot Big Bang. During inflation, space was saturated with energy, devoid of matter and radiation, and expanded exponentially. However, inflation couldn't have persisted indefinitely and must have emerged from some pre-existing non-inflationary state. Unfortunately, our knowledge of this earlier state is limited, aside from knowing many things it couldn't have been. We don't live in a universe where matter drifts in empty space. We live in a universe filled with energy fields that interact to form everything we see. When considering the vastness of emptiness, the endless void, and mortality, it's striking how the idea of nothingness can provoke such fear. Did William Shatner, at 90, go on a space journey expecting to find the universe's mysteries, only to realize there was no mystery or grandeur? He encountered only death, witnessing a cold, dark, black void unlike any darkness on Earth. It was overwhelming and all-encompassing. Yet, in another paradox of nothingness, Shatner wasn't truly observing a void. Rather, he was looking at a vacuum where a lot was happening that he couldn't see. Quantum field theory, one of the most accurate theories in physics, predicts the outcomes of many experiments. According to this theory, the universe is not made of matter floating in empty space but of energy fields that permeate space and interact, creating everything we observe, including ourselves. Some physicists describe these fields as fluid-like, similar to water in a pool, while others compare them to a room filled with varying levels of energy, like a field of distributed heat. These fields are constantly moving due to quantum fluctuations, brief changes in energy similar to ripples in a wave caused by external forces exciting the particles within the field. For example, an electromagnet can cause changes in an electromagnetic field. Even in their lowest state, known as the vacuum state, fields remain active. Pairs of positive and negative particles continuously borrow energy from the vacuum, briefly appear, and then disappear, returning the energy. These temporary entities are called virtual particles. When the field is excited or at a higher energy level, it has ripples or waves that produce elementary particles that persist and interact with each other, forming the world we know. The type of particles created depends on the field. Different matter particles are associated with specific types of fermions, such as electrons, up quarks, down quarks, and neutrinos, which are fundamental components of all atoms. These fermions interact through three types of fields: electromagnetism, involving photons, the strong nuclear force, involving gluons, and the weak nuclear force, involving W and Z bosons. According to Cambridge theoretical physicist David Tong, without these force fields, matter particles would drift aimlessly in the universe without interactions or interesting behaviors. Then there's the Higgs field, which Tong compares to molasses spread throughout the universe. The Higgs field gives mass to other particles, stopping them from moving at the speed of light. Tong notes that this comparison is not perfect because it suggests friction, while in reality, different particles interact with the Higgs field in various